Hello and welcome to a next lesson on electricity, which is series and parallel circuits. This is lesson 9 in the electricity topic, and my name is Mr. Pratt, Director of Science for Outward Grange Academies Trust. So for the lesson you're going to need a pen, some paper or an exercise book so you can record some notes, and we've got a few examples for you to try. A calculator, because there's some calculations using the equation for potential difference current and resistance in this lesson. And unless you're needing to watch this video on your mobile phone, get it out of the way, get it on silent, try and avoid all the distractions that you can. I'm going to give you 2 minutes then to try and recall, and it might be a while since you've seen these symbols, as many of these electricity circuit symbols as you can. You'll probably find that 5 or 6 are pretty straightforward, and it'll just be a matter of trying to remember the other tricky ones. 2 minutes. Okay, just 45 seconds left. Should just be finishing off. If you manage to get 7 out of 14, that's not bad. 10 or more, that'd be fantastic. Let's see how you've done then. So top 2 switch, so we've got the open switch, looks like a bridge that's open, so that would be off, and then the switch that's closed, on. Cell and battery, you might have gotten the wrong way round. If you're in a prison cell, you've got one room. Battery, a battery of guns means lots of guns. If you get battered, you've got hit by multiple punches. Battery farming is when you've got lots of cages all fastened together and joined up. So cells 1, batteries lots. Tricky one, that's a diode, allowing current to flow in one direction, left to right in that diagram. All the ones that are rectangles are resistors of some description. That's just a straightforward fixed resistor, so you might see that in a circuit with 10 ohms written next to it. Next one, we've got a resistor that we can change, like a dimmer switch. That's a variable resistor. Lamp or bulb. Next one, type of resistor, but it's a resistor with a piece of wire through the middle that can melt when the current gets too high. That's a fuse. A couple of easy ones, voltmeter for measuring potential difference, and ammeter for measuring current. Another type of resistor. This time it's a resistor that changes when the temperature changes, so we mix the 2 words together, the 2 words temperature or thermometer and resistor, thermistor. I always remember it as an ice hockey stick, and then that'll remind you that it's cold, so it'll have a different resistance when it's cold. And then a different type of resistor, last one, a light dependent resistor. No, it's not the last one, because over there's a different type of diode. It's a diode that gives off light, so we call it an LED, a light emitting diode. Give yourself a mark out of 14. If the ones that you've not got, those are the ones that you probably need to make a note of and try and remember them. If you've remembered them already, then I wouldn't bother writing them down. Two outcomes then. We're going to describe the differences between series and parallel circuits. You've looked at series circuits before, and you might remember lower down the school looking at a straightforward parallel circuit. And then the other outcome, we're going to use the equation V equals I times R to calculate unknowns in a circuit. So we're going to make sure you're all right with that equation, and that's an equation that you need to memorise. And we're going to use it to find unknown values in circuit diagrams. So 2 minutes then, might not take you quite so long. I want you to draw one diagram that's got two bulbs in series controlled by a switch. You'll need a cell in there as well. And then for number 2, the same again, two bulbs and a cell, but this time I want you to put them in a parallel circuit. There's different places you could put the switch. I want you to put the switch in a place that puts both of the bulbs on and off. 2 minutes. Okay, you should have done your series 1 by now. Just be finishing off. Just look carefully where you've put your switch in diagram 2. You should have something that looks like that. So we've got the series 1 on the left, parallel 1 on the right. I've actually put a battery in those. If you've just put one long line, one short line, you put a cell in, that's fine. Just look at your positioning of the switch. So in the series circuit, if you open and close that switch, you'll control both bulbs because the current has only got one route round. In the parallel circuit, where I've put that switch, it wouldn't matter if I put it anywhere along that line that it's on, or even on the opposite side there, going back to the cell. It wouldn't make any difference. It'd still do the same job. That controls both bulbs because the current has to go through that bit of the circuit. If I'd put the switch next to each bulb in the branch, the cell would just control the bulb that it's next to, and that's how the wiring works in your house. So hopefully when you put your bathroom light off, it doesn't put off all the lights in your whole house, because that would be grim. So you have a switch next to each particular bulb, and your house would be wired in parallel so that you've got lots of separate circuits in there. Got two circuits here, both using all the same components, so the bulbs are the same and the cells that we've got are the same. The difference is I've set up the one on the left here as a series circuit, so you've got one component after another, like a series on TV. You've got one and then the next one, and the circuit on the right is a parallel circuit, so we've set it up so it's got branches that are parallel. But everything that I've used is the same, it's just the way that it's been set up that's different. What you need to understand is in a series circuit, the potential differences in the current are a little bit different around the circuit than they are in a parallel. So to understand any circuit, you need to think about the resistance, which you've done in year 9 and will be doing again later. The potential difference, which we measure in volts, sometimes you call it the voltage, but potential difference, it's an electrical push that the cell or battery is providing. And then we've got the current, which is flowing around, which is caused by movement of electrons. In these two circuits, we've got arrows that are representing the conventional current. And conventional current runs from the positive side of the cell all the way around the circuit and back into the other end, into the negative side of the cell. So that's the same in both circuits. If I just flick these so that I'm using circuit symbols instead of pictures of the components, the large line represents the positive terminal of the cell. I'll go back because it's probably slightly easier to understand it doing this way. What we'll look at first then is the potential difference and how that varies in a series and a parallel circuit. So I've got a voltmeter here. So what I'll do first, I'll just put the leads of the voltmeter just across the cell, and then we can see what potential difference that the cell is providing, and that's 9 volts. So think of that as a 9-volt push that it can push the circuit, the current around the circuit. I'll just check the other one. Let's just check that's the same. Yeah, so we've got 9 volts potential difference total in each type of circuit. If I then put the voltmeter across both cells, let's make it easier to see, across both bulbs, you can see that adds up to 9 volts. So the total potential difference that we've got here, 9 volts across your 2 bulbs, is the same as the cell. Well, that makes sense because that's where the potential difference comes from. So we've got 9 volts across both of those. But in a series circuit, the potential difference is shared across the components. So if I just put these connectors there for the voltmeter across one, you can see there's only 4.5 volts there. So there's 4.5 volts across that bulb and 4.5 volts across that one. But if I then flick over to have a look at the potential difference across each bulb in the parallel circuit, you'll notice that it's still 9, because in the parallel circuit, the potential difference isn't shared. If you think about it, this bulb here, the top one in the branch, is connected directly with the leads to the cell. So it's got all 9 volts, but so is the bottom one as well. So the bottom one has also got 9 volt potential difference across it. That then explains why, if you look, the yellow lines coming off the bulb represent the brightness, that connecting them in a parallel circuit, they're brighter. They're producing more power in the terms of light and heat. So I'll say that again, potential difference is shared across the components in a series circuit, so we've got 4.5 each, and in a parallel circuit it's got the full 9 volts. You don't need to write anything because I'll give you a summary slightly later on in the lesson. So that's potential difference covered. While I'm here, you'll notice over here we can add some wire resistivity. If you were to do this experiment in class, it still works fine, but the numbers are never quite perfect. And that's because in the real world, the wires themselves, the leads themselves, have got a little bit of resistance. So if I now put that across there, you'll notice I've only got, let's make it a little bit less than that. You'll notice it's not quite 9 volts because there's some of the potential difference that's across the leads themselves, and the same down here. And then if I put it here, it'll no longer be all of the 9 volts because of the resistance on there. So just bear in mind, if you do this practically in a lab, you've got to think about it. The numbers won't be perfect, and that'll be the same when we look at current in a minute. But I'm going to get rid of that for now because I don't want to overcomplicate things. So that's potential difference dealt with. So let's just put the voltmeter out of the way and let's look at current. So I'll put an ammeter in this circuit now. There we go, let's tidy it up. So we've got a current of 0.45 amps in that circuit now. So potential difference, remember it's still the same, it's 9. So potential difference is pushing the current round, and we've got 0.45 amps. Let's put that, well, instead of putting the ammeter in a different place, let's just put another one in, make life easier. Let's put another one in there. So it's the same. So it doesn't matter where I put the ammeter in this series circuit, it's always going to have 0.45 amps in it. So it's 0.45 amps all the way around. That's worth knowing because sometimes that's quite a simple question in the exam. It'll tell you what the current is over one side and it'll just want you to say what the current is over on the other side. So there's no current lost. It's not escaping. It's not coming out. It's just flowing all the way around. Let's do the same in the parallel circuit because that's slightly more complicated. So what I'll start off with, I'll put one in here first. Okay, slightly wonky. So I'm going to see if I can get it a bit straighter. Don't like it too wonky. There you go, I'll just take. So that it's not connected, so it won't make any difference. Right, okay. So that's interesting. So even though I've got the same components in the series circuit on this side and the parallel circuit on this side, I've got a much bigger current flow in here. I've got 1.8 amps flowing through there. Well, let's see if it's the same all the way around. Let's put another ammeter over this side. Let's see what it's like over there. Okay, so that's the same. So we've got 1.8 amps on the side coming out of the battery and 1.8 amps going back in. That makes sense. The same amount coming back in is going out. It's not disappeared anywhere. Let's have a look at the two separate branches then. Let's have a look at the current in there. Right, so now we've got 0.9. So it's less coming down this branch than we had to start with. Well, if you look at that number, you might notice something about that number. We've got 0.9 in that bottom branch and then 1.8 going in and out of the battery. So it's less. So where must the other bit have gone? Let's put another ammeter in there. And that's 0.9 as well. So that makes sense then. So we've got 1.8 amps coming out, and then that 1.8 amps divides up. Some of it can go that way, some of it can go that way. And because the bulbs are identical, the resistance is identical, it's just as easy to go along the top branch as it is to go along the bottom branch. So it just shares out. So 0.9 amps goes along the top, 0.9 amps goes along the bottom, and then it goes round and they join back up and the whole 1.8 amps flows back into the cell. So in a series circuit, the current's the same all the way around, and in a parallel circuit, you get a large amount of current coming out of the cell, and then that'll divide up along the way. If you look at the current now, we've got twice as much current going through our bulbs in the parallel circuit as we have in the series circuit, which is again why they're brighter. There's more electrical power going through there. What we'll do now is we'll get this as a summary, and then I'll give you some fairly straightforward examples to have a go at. Here's a summary then. So we can join components in a series or parallel circuit. In a series circuit, they've only got one path. Parallel circuits have got separate paths, they've got branches, and then they'll join back up again before they go back into the cell. So in series, the total potential difference is shared between the components. So in this one that I've got here, if I add 9 volts there, I always find it easy to explain by putting some numbers in. If I've got 9 volts total across the cell, that 9 volts will be shared across the components, and we've got our components are two bulbs. If the bulbs are identical, we'll have 4.5 volts across each. 4.5 plus 4.5 gives you the 9 that you've got altogether. And when we're talking about current then, this is straightforward. In a series circuit, there's no different paths for the current to follow, so the current will just be the same everywhere. So in this one, we'd have 0.45 amps all the way round. So in a parallel circuit, because the components are connected directly to the cell, they've just got the same potential difference as the cell. So in this one, if we've got 9 volts across the cell, we'd have 9 volts across that bulb and 9 volts across that bulb. The current, though, is different. The current that comes out of the cell and goes back into the cell is the same. So we could have 1.8 amps coming out of the cell and 1.8 amps going back in. But along the way, it'll divide up. So if the bulbs were equal resistance, we'd have half of it going that way, so that'd be 0.9, and the other half going down the other branch, going around there, and then it'd join back up to give us the 1.8 to go back into the cell. You might find that a quick diagram of that is helpful. You could either pause the video and do that now for your notes, or it's on the summary slide at the end, and pause it at the end, and then you can just make a summary using that. Quick progress check for you then. See if you've got it. 1 minute. What I want you to do here is to fill in the 2 missing current values and the 2 missing potential difference values. It should only take you a minute. Assume that your 2 bulbs are identical. Just 10 seconds. You should have found the current values dead easy if you've remembered how the current works in a series circuit. So let's do those first. So the current is the same everywhere in a series circuit, so it's as simple as just copying it out. We don't have any leaking out, we don't have any escaping, we don't have any jumping out of the wires, so it's 0.2 amps all the way around. So give yourself 2 marks if you've got those 2 right. Potential difference. The potential difference though is shared, and we've got 4.5 altogether at the cell at the top, so that 4.5 must be shared, and if the 2 bulbs are identical, it'll just be shared equally. So half of 4.5 is 2.25, so you get 2.25 volts across one and 2.25 volts across the other, which gives you a total of 4.5. So give yourself another 2 marks if you've got those right. Well done. Trickier now. Let's have a look at a parallel circuit. Again, I want you to fill in the 4 values there. There's 2 current values to fill in and 2 potential difference values to fill in. If you manage to do it in the time, can you remember the equation? It's actually at the top of the slide there, V equals IR. And can you use it to work out the resistance of one of the bulbs? They are both the same, so you only have to do one of them. Just 10 seconds left. Right, let's have a look at the potential difference first. Potential difference in a parallel circuit across each component is just the same as the cell or the battery that you've got at the top. Because if you follow the wires, there's no other components that have got resistance or are in the way. So it's connected directly if you follow it back. So it doesn't matter what the other bulb's doing, it's just connected itself. So we get 3 volts potential difference across the bottom one and 3 volts potential difference across the top one. Give yourself a mark each if you've got that right. Current then. We've got 0.30 amps coming out the positive side of the cell. It comes down here and then it divides up. If we're saying the bulbs are identical, it'll just split half the current down one branch, half the current across the other branch. So that gives us 0.15 going through there, 0.15 going through there. 2 more marks if you got those right. If you manage to do the extension, calculating the resistance, just pick one of the bulbs, and then what I want you to do is to use the values for that bulb. So if we pick that one, we pick the top branch, doesn't really matter, same for both. We've got 3 volts potential difference across it, so V equals 3. The current flowing through it is 0.15 amps, so we need to use those values. So the resistance is volts divided by amps, so the resistance of that bulb will be 3 divided by 0.15, which will give you 20 ohms. So both the bulbs in that circuit have got a resistance of 20 ohms. Amazing if you got that right. Well done. I'm going to have a go now at using this equation a little bit more. That's how it appears in the specification. So potential difference equals current times resistance. Most potential difference in volts, current in amperes or amps, and resistance is in ohms, which is the Greek letter omega. Worked example then. I will let you look at it first before I fill it in for you. But we've got here, it tells us the current flowing through a 22 ohm bulb is 0.10 amps, and we have to find the potential difference across the bulb. So V equals I times R. We know that the current I is 0.1 and the resistance R 22. So the potential difference is 0.1 times 22, which gives you 2.2 volts. Underline the answer to draw the examiner's attention to it. If you want to use that as a worked example, pause the video and write it down. Worked example 2, bit trickier. Same equation though. Current flowing through a resistor is 0.25 amps when a potential difference is 4 volts is applied. This time I want you to find the value of the resistor. Same equation, V equals I times R. So you write your equation out. You've got to recall it, you've got to remember it. If you don't remember it, get yourself some flashcards or write them all out and just keep practicing till you've got them all right. So 4 volts equals 0.25 amps times R. So 4 equals 0.25 times R. So if 4 equals 0.25 times R, what must R be to give you 4? So R is 4 divided by 0.25, which gives you 16 ohms. Underline it to draw the examiner's attention to it. We've got this simple series circuit then, and we've got some values on there. What I want you to be able to do now is to use the equation V equals I times R to find unknowns in a circuit. So let's have a look at this series circuit then, thinking about V equals I times R at the same time. So we've got 20 volt cell delivering 2 amps through a 10 ohm resistor. And we can see we've got the voltage across that 10 ohm resistor is 20 volts because we've just got one bit in the circuit, so one component in the circuit, so it will have all of the potential difference from the cell across it, assuming that we're not losing any energy through these wires. Just while I remember, we've got on here the conventional current flowing. So it's flowing from positive, which is the big line on the symbol, round, all the way around to the negative. So conventional current comes out the positive, goes round to the negative. Just so you understand, though, it won't occur in exams really, but if I show the electron movement on that diagram instead, because electrons are negative, it's electrons that are moving from the negative side to the positive side. So if we're talking about electron movement, we're coming out of the negative. But let's stick to conventional current, so the current is flowing from the plus to the minus. So if we think about the wave equation, think about the equation for resistance. So V equals I times R. Here we've got V, which is 20. So 20 equals the current 2 times 10. So 20 equals 2 times 10. That's right. If I increase then the value of this resistance so I can make it bigger, let's double it. So I'll double it from 10 up to 20 ohms. And what we've got now, because we've doubled the resistance, it's making it more difficult for the current to flow through. That's what resistance means. So instead of having the 2 amps that we had before, we've only got 1 amp. But the equation still works because 20 equals 1 times 20. So increasing the value of the resistance will decrease the current. There'll be less flowing around. So let's keep the resistor at 20 ohms then. But this time let's make the voltage smaller. Let's reduce it to 10 volts first. So reducing the potential difference means that you've got less push forcing the electrons around the circuit. So because we've got less potential difference, we've now got less current again. But the equation still works. V, 10, equals I, 0.5 times 20. 0.5 times 20 is 10. What you'll probably get asked to do is a sort of problem solving question. So there'll be missing values on a circuit. It could be a series circuit or it could be a parallel circuit. And with those missing values, we've got to work out what they are. Most of the time, that'll involve using V equals I times R. In fact, students that I teach, I generally ask them to remember the equation a different way around because it's often more useful. If you remember that the resistance is the potential difference divided by the current, so the resistance, 20, is 10 divided by 0.5. If you remember it that way around, the reason that's more useful is because quite often in the exam, they ask you to work the resistance out, so you don't have to move anything around in the equation if you remember it that way around. So let's take out something then. So let's take the values off. Let's just make that. So you might be, let's put it all the way up to 100. Put that in there. So let's take that off. So we've got a question now. And the question tells you what value of current. So it might be marked on an ammeter, it might just tell you in the question. So we've got a current of 0.1 amps flowing through it. Then they might have a voltmeter connected to the cell there. And now the question asks you to find the value of the resistor. So the equation's V equals I times R. We know the potential difference, it's 10 volts. We know the current, it's 0.1 amps. So we can find the resistance. If you've remembered the equation of resistance equals potential difference over current, it's dead easy. So you're going to do, right, the resistance is going to be 10 divided by 0.1. So that gives you 100. So that will be 100 ohms. And you've done that question, no problem. Let me just take that out a minute and let's make it slightly more complicated and see how you do with that one. And then we'll have a go at a few examples leading up to a exam question in the end. So let's put 2 in. Well, I don't like it when it's wonky. Anyway, we'll live with it. So we've got two resistors in there. Let's put that across there. Across there. So we've got a potential difference of 10 volts and we've got a current of 0.09 amps. Now what happens is if we use the equation V equals I times R, or we use it with the version resistance equals potential difference over current, so R equals V over I, we can work out what the resistance is in that circuit. And if we work the resistance out, we'd do 10 divided by 0.09 and we'd have a value. But that's not a value for the individual resistors because we've got two in there. What we need to be able to find the value for the individual resistor is to make sure that we have the potential difference across the resistor that we need to find. So when you've got a calculation question or a problem solving question where you need to find a value, big tip for you, what I want you to do is to just, whenever you've got to, for example, find that resistance, you need to use the current flowing through that resistor there, which is 0.09, and the potential difference across that resistor. So not anywhere else in the circuit, not across here or not across there or not across anywhere else. It's got to be the potential difference across there. So if you concentrate on that particular bit of a circuit, it doesn't matter how much complications you've got. So if you've got a parallel circuit, it might be quite complicated. You just need to use the values for V, I, and R at that point in the circuit, and you should be able to do any of the problem solving questions. Another progress check then. 3 marks for this one. I want you to find the potential difference across the 4 ohm resistor. Just a reminder, think about what the current is in that circuit. You know the equation still at the top of the screen there. I'll give you 1 minute. So it's V, potential difference we're finding. Halfway through your time. We've got 4 volts across that battery then, but we need to find the potential difference across the 4 ohm resistor. So it's going to be less than 4 because some of that 4 is going to be shared across the 8 ohm and then the rest of it is going to be shared across the 4 ohm. In fact, because it's more difficult to get through the 8 ohm, there'll be a bigger potential difference across that one. So we're just going to use the values that we've got for this. So self-assess what you've got. We know the current is 0.33 amps and that's the same everywhere. So we know that we've got 0.33 amps flowing through both resistors, including the 4 ohm. And we're going to use the 4 ohm value. So in a series circuit, the current's everywhere. So we know that it's 0.33. We're going to use V equals I times R. So the potential difference is 0.33 amps times the 4 ohms, which gives us 1.32 volts. There's 3 marks for that. 1 mark will be for V for the unit. Give yourself 3 if you've got that right. Number 2. First of all, I want you to find the potential difference across each of the 2 bulbs and then the current flowing through the bulbs. Even though that's worth 4 marks, I'm only going to give you a minute because it's pretty straightforward and it shouldn't take you long. Don't want to waste too much time. Halfway through your time. Let's look at question 2 first. So we've got 4 volts total across the cell, and that 4 volts is going to be shared. And because the bulbs have got the same resistance, they're both 1 ohm, it'll be shared. So in a series circuit, potential difference across the cell is shared across the components. So we'll have 2 volts across that one, 2 volts across that one, which gives us the 4 that we've got total at the top. Mark each for those. So 2 volts and 2 volts. For question 3, back to that tip, pick the values that you've got at a particular point in the circuit. So I'm just going to pick one bulb. It doesn't really matter which bulb that you pick. So on this bulb here that I've highlighted, V equals I times R. So V is 2. We've got 2 volts equals I times 1 ohm. So 2 equals I times 1. What must the I be? Well, it's 2 over 1. It's 2 amps. So it'll be 2 amps through both bulbs because the current is the same everywhere in the circuit. Don't forget to underline your answer to point the examiner's eye to it. Last progress check before we have a look at an exam question. So question 4 and question 5, just a minute for the first one. And if you do the first one, we'll self-mark it together. And then we'll do the second one, question 5, later. So we've got a parallel circuit there. It looks quite complicated, but don't be put off. So for question 4, it's 3 marks. I want you to find the potential difference across each of the 3 resistors. So we've got a 2 ohm, a 3 ohm and a 4 ohm. 1 minute. You'll kick yourself if you've not got this right, because it's a lot more simple than you think. We've got 12 volt potential difference across the cell. And because this is a parallel circuit, in a parallel circuit, the potential difference across the components is the same as across the cell. So they don't share it. They're all connected individually to that 12 volts. So across the 2 ohm resistor, we have 12 volts. Across the 3 ohm resistor, we have 12 volts. And across the 4 ohm resistor, we have 12 volts as well. So you've got 1 mark for 12 volts, 2 marks for 12 volts, and 3 marks for 12 volts. I'm going to give you 2 minutes now for question 5. And I want you to calculate the current through each of the resistors. So the current through the 2 ohm, then the current through the 3 ohm, and the current through the 4 ohm. Don't forget, use the values at that point. So when you're trying to find the current through the 2 ohm, use the values that you know is going for the 2 ohm. Don't worry about anything else, just have a look at that resistor individually. So 2 minutes. Minute left. See how you've got on then. Let's do the current through the 2 ohm resistor first. So we're going to focus in on that bit of the circuit, and we're going to use the values from that bit of the circuit. And we know we've got a resistance of 2, and we know we've got a potential difference of 12. So V equals I times R. So 12 equals the current I that we don't know times 2. So if 12 equals I times 2, I must be 6 amps. So we've got 6 amps flowing through that bit of the circuit. Now you do the others in the same way. I'm just going to jump to the bottom branch, the 4 ohm there. We can do this without any calculation because the resistance is double. If it's twice the resistance in that bottom bit, the current going through the 4 ohm will be only half. So we'd end up with 3 amps there, and that's because we'd get 12 divided by 4. And then for the middle branch, through the 3 ohm, we get 12 divided by 3, which is 4. So we get 4 amps in that middle one. For those of you who are trying to get your heads around it a little bit more, that would mean then that the amount of current that was coming out of the cell it'd have to be 6 plus 4 plus 3, so that'd be 11 amps. So you'd have 11 amps coming out of the cell, and by the time it's gone all the way around and joined all back up again, you'd get 11 amps going back into the cell. Quick look at a fairly straightforward exam question then. It does look a lot more difficult than it actually is. I'm not going to read it out. I'm not going to give you much information. I just want you to think the way that we've done things before. And it's 2 marks, 1 minute. There's 10 seconds left. So it tells us it's 0.1 amps flowing in that circuit. So it's not giving us the value next to the ammeter or in the ammeter. It's just told us that it's 0.1 amps. So that current is the same everywhere. So that means we have 0.1 amps flowing through our 45 ohm resistor. So that's what we're bothered about. So we've got 0.10 amps, and we've got 45 ohms. So we use the formula V equals I times R. That'll give you a mark. Substitute your values in. So V equals 0.1 times 45, so your potential difference is 4.5 volts. So we've got 4.5 volts across the 45 ohm resistor. So we don't need to do it for the question, but if you look back at that circuit there, it's 12 volts altogether. So we know we've got 12 volts across the 12 volts across all of it. We've got 4.5 volts across the 45 ohm. There'll be a part B in this question where it'll ask you to work out what the potential difference is across R, and we know what it's going to add up to. It's going to add up to 12. There's a simple way of doing it there. Can you see we've got 4.5 across the 45? So therefore we'd have 6.0 across the 60 ohm. So 6 and 4.5 is 10.5, which leaves you 1.5. So there'd be 1.5 volts across that resistor R. Second exam question. Again, just 1 minute. Right then, so A part 1 asks you what the potential difference provided by the 4 cells. So we know each cell provides a potential difference of 1.5 volts. And we've got 4 of them. 1, 2, 3, 4. So we have 4 cells, 1.5 each, so it's 1.5 times 4, so we get 6 volts, 1 mark. And what will the reading be on the voltmeter? Well, because it's a parallel circuit, the reading on the voltmeter, so the voltmeter is reading the potential difference across the 60 ohms, well, it's just going to be 6 volts because it's the same as it is across the cell. It'd also be 6 volts across the bulb if you looked at the bulb. 6 volts, 1 mark. I'll leave you with a summary then. So we've got a diagram of the 2 types of circuits. Probably the most important thing. For components connected in series, the current's the same everywhere. It's the same through each component, but the potential difference is shared between the components. And then the parallel circuit, the potential difference across each of them is the same, but the current branches out and then adds back up again. Also, important bit, when you're doing a calculation question that's got a circuit, just concentrate on the bit of the circuit that you're bothered about. Try not to be put off by the other bits. See you next time.